All right, 1.4, we're talking about continuity and one-sided limits. And the first type of continuity we're going to talk about is continuity at a single point. So if we have a function that's continuous at C, or I'm sorry, we have a function, it is continuous at C when the following are true. So these are the three conditions that we need in order for a function to be continuous. F of C has to be defined. In other words, I've got to be able to plug the value in and it works. I can't just get a 0 over 0, right, or something like that. It has to work. The second thing is that the limit from both sides has to exist. So I have to be able to approach from the left and approach from the right and arrive at the same value from the right and the left. And then the last thing is that value that I approach to from the right and the left has to be the same as the function value when I plug C in. So let me kind of show you about what of these things are sort of eliminating the possibility of. So the first thing is eliminating the possibility of simply a hole in the graph. If I have a hole in the graph, it's clearly not continuous, right? It breaks. I mean, even at that split spot, it breaks. The limit business. Well, if I don't have the hole in the graph, but I have something that has a jump in the graph like this, so there's a hole down here, but there's a filled in circle right here, this doesn't work because the limit from both sides doesn't come up to the same place. Right? The limit from one side is different than the limit from the other side. And the last one is eliminating the possibility where there's the hole like this, and it's doing this, but it fills it in somewhere else. So it has an existing limit. It's the dot. Right? Not a limit, a function value, the dot. It has the limit from both directions, but they don't match each other. I have this discontinuous piece. So these are the three things that cannot happen. These are all not continuous. And then if we extend that idea just a little bit, instead of just talking about continuity at a single point, we can talk about the continuity on an interval of points. We have the following. A function is continuous on an open interval AB when it's continuous on each point in the interval. And a function that is continuous on the entire number line from the negative infinity to infinity is called everywhere continuous. Okay, so we're going to do a few examples of finding limits. And the first one we're going to look at looks like this. So the directions say find the limit, and then it says if it exists. And if it doesn't exist, we need to explain why not. So this is a one-sided limit. We've seen this notation before. It's one-sided because it's got the sign after the number. This is a positive sign. It doesn't change how we evaluate this function. You can do this in any way because it doesn't say how you have to do it. So if you really want to draw a graph, go with a graph. If you want to do a table for numerical values, you can go with a table. But to be perfectly honest, the quickest way to do it is the algebraic way, which is to just put the number 8 in for x. Okay? So as long as I'm able to do that, which I am, that will be the limit. If I put in, say, negative 8, it'd be a problem on this, right? Like if this said the limit is x that goes to negative 8, we would have a problem, and then the limit would not exist, and then we'd have to justify why. And you could justify why saying there's a 0 in the denominator and I can't divide by 0. You could justify by why from a graph saying, look, there's an asymptote at the graph. You could justify from a table and say, oh, look, the values go to infinity or negative infinity as I put in increasingly closer values to the one I care about. So any of those justifications just depends on what you're using as your method for trying to figure out whether the limit exists. This one exists, and it's equal to 1/16. So the quickest way to do it is to simply plug the value in if you're able to do so. Is that all right?
And the plus means it's coming from the left, right?
Yeah, it means that it's coming from the right, from the positive side of the graph. Yeah, so this value right here, the little positive afterwards, doesn't actually change how we process the problem. It does mean that it's coming from the right-hand side, but the fact that it's coming from the right-hand side doesn't affect this particular problem. If the limit does not exist, then it would, because like if it were getting infinitely large or infinitely small, then we'd have to be a little more careful. So what happens on this one? This one's 9 from the left because it's negative. What happens on this one when I try to plug in 9? Yeah, I get a 0 on the top and the 0 on the bottom. Okay? Now, we learned about that in section 1.3. When we got a 0 on the top and the 0 on the bottom, that means that there's some way to manipulate this so that that doesn't happen. And in particular, what we want to do to manipulate this is we want to use conjugates. How do I know? Because there's a radical in the problem. Right? That square root of x tells me I'm going to use conjugates. So what is the conjugate of the numerator? Because the numerator is the problem. That is where it's got the square roots. Good. Square root of x plus 3. And so I have to do that on the top and on the bottom to multiply. Now, I don't ever actually distribute the denominator out, right? The part that has the radical is being put, like this conjugate is being put in to help simplify the numerator. It's really not about the denominator, right? The radical's not in the denominator. If it were in the denominator, it would be about the denominator. But it's about simplifying the piece that's got the radical in it. So whenever I'm working with these problems, I don't want to distribute the piece that doesn't have the radical, that's my x minus 9, into the piece that does, square root of x plus 3. I just want to write them beside each other. They'll clean themselves up all by themselves, and in fact, if you distribute them, you're going to make it really hard to figure out how to clean it up. It will not be as easy to identify. On the top now, though, we do want to clean this up, because the whole point in multiplying by the conjugate is to eliminate the radical. So this is like difference of squares. I only end up with the first two terms being squared or multiplied by one another, and the last two terms. So what is the square root of x times the square root of x? It's x. What is the negative 3 times the positive 3? Negative 9. So remember, the reason this happens is because the inner and the outer terms are identical except for signs, so they add to 0. And that always works if we're using the conjugates. That's a really good place for our problem to be. Do you see anything that will reduce? Yeah, this entire numerator matches this piece in the denominator, right? So we are able to reduce them and cancel them out, leaving me with a 1 on top and a square root of x plus 3 on bottom. And then still my limit is as x approaches 9 from the left. Now can I plug in 9? Yes, I can. So I have 1 over the square root of 9 plus 3. What's the square root of 9? 3. And 3 plus 3 gives me 6. So this limit is 1/6. Okay, conjugates. Anytime you see radicals, that's got to be where your head goes. Got to go to conjugates. Okay, we're going to do one more today and be done a little early. Is that okay with you? Okay. So our last one for today. Explain why, or sorry, find the limit, explain why it exists, or explain why if it doesn't exist. We already talked about this one. This is the first place where it actually matters which direction we're coming from. Notice, if you would, if you put in 0 on the top and the bottom, we get 0 over 0, right? So there's got to be a way to reduce this, but the fact that there's an absolute value means that it matters whether the values we're putting in are positive or negative, correct? That absolute value changes things. So think about with me, I'm looking at 0 from the left here. So are the values I'm putting in bigger than 0 or smaller than 0? Smaller, and smaller than 0 values have the sign that is negative. So this is coming from the left, so my x values are negative. We'll talk about the graph of this too in a minute. I just want to talk through this with you with algebra. These are negative x values. So what is the absolute value of a negative number? We'll just take one for instance. Let's say we had absolute value of negative 5. What is that?
5.
It's 5. So what is the absolute value of negative 10? 10. And probably in your mind, you're thinking, I take off the negative. Agreed? Yeah. Well, the problem is that if I look at the x right here, while x is negative, I don't see the negative in the problem, right? It's not present there in the notation, but it is negative. So when we're dealing with an absolute value of x, what we do is we talk about the fact that x is either x, and this happens when x is greater than or equal to 0, or it's equal to the opposite of x, and this happens when x is less than 0. So it feels like I'm like putting a negative into the problem. The reason that is the case is because when I put a negative onto a 5 that's already negative, what happens? It makes it positive. So attaching an additional negative changes the sign, just like eliminating it by pulling it off, the way we think about it, eliminates the sign. And it's the only mathematical way that we have to represent that well. So we're going to change our problem to represent this negative x because we're dealing with x values that are smaller than 0. So our expression that we have to begin with, the limit as x approaches 0 from the left, is going to change to say negative x over x. I'm removing the absolute values. I'm putting in the negative x because these are the negative values, right? Values to the left of 0. Can I reduce negative x over x? It can. How will it reduce? Just to negative 1, right? And there's no more x to actually plug in at 0, so it really just is negative 1. Now, if this had been x approaches 0 from the right, it wouldn't be negative 1. What would happen, this isn't our question, but what would it happen if I was asked to do x approaches 0 from the right? Yeah, I'd have an x on top because it'd just be by itself, the same as it was, right? I'd get a positive 1 instead. So this graph is an interesting one, a little bit different than most of them that we'll deal with because it isn't continuous. It actually has, that's not great, but we'll pretend for now. This is at 1, and this is at negative 1. And it has a closed-in circle here, and it has an open circle here. This is my graph. So you can see that if I'm approaching from the left, I do stay at x equal negative, I'm sorry, at limit of negative 1. And if I'm approaching x equals 0 from the right, I do stay at a limit value of positive 1. Does that make sense? And you can make your calculator graph this too. So if that's of interest to you, let me know, and I'll just work with you one-on-one. But it's not the only way to do the problem. You can reason through it algebraically. Now, the question itself above asked, find the limit if it exists, if it does not explain why. This one-sided limit did exist, negative 1. The one-sided limit from the other direction exists as well. But if they asked us just to do this limit as x approaches 0, it would not exist, correct? I'd have this jump in the graph at x equals 0, and I'd have to say it does not exist. And descriptively, I could talk about the fact that from the left it's equal to negative 1, from the right it's equal to positive 1. They're not the same. I could talk about the fact that there's a jump in the graph if I think about it visually. Either of those would be good options. You could do it from a numerical perspective too. Any questions on that? All right, so homework from 1.3, since we finished that earlier today, will be due on Wednesday next week. We've got a whole weekend and everything to do it. The Success Center will not be open again until Tuesday night. Okay, so they're going to shut down for the weekend as well, just like for you. Yeah. So Tuesday night, if you need help, you can get help from them. If you need help while you're working over the weekend, feel free to send me an email.